Well, let's get started. All right. Welcome, everyone. Hope you're having a great start to your Saturday. Today, we'll be talking about natural language processing and how it can be useful for you, students and hackers. I'm Tommy Zhao. You can connect with me at Tommy Zhao on Twitter. And the first question I want to ask is, first of all, can I get a raise of hands? How many of you have experience on this topic? Hopefully none of you, so this will all be new information, but I'm curious. All right, it doesn't look like anyone's got prior knowledge on this, so all right, so I'll continue as normal. So I'm Tommy Zhao. There isn't too much to say about me other than I'm a student here at Penn State. I study computational data science, and I've used natural language processing a lot for various projects, some research, and some internships. And I'm a big AI/machine learning guy, so this is kind of what I'm interested in. Anyways, so what is natural language processing? Well, if you ask Wikipedia, it'll tell you it's a subfield concerned with how computers and humans interact. In particular, how you can get computers to program or to process large amounts of natural language data. And that's important because no one wants to read, 10,000 Amazon reviews or, moderate a Discord. We can have computers do that. Before we get into processing natural language, we have to ask, well, what is language? How do we get computers to really understand human speak? And there's no simple answer to that question. I mean, people have been thinking about this for years. I want to give you a brief history of what we used to think of language up until the computing age. So there's this guy named Aristotle. Back in the day, he thought a lot about this stuff, and he came to the conclusion that language was essentially meaningful spoken language, and that written words are just symbols of sound, which is, pretty good definition of language until you get into the modern age where we have computers, and all of a sudden it's like, how do you get a computer to understand these quote symbols of spoken sound? Well, there's this guy named Noam Chomsky, famous linguist, very famous, and he came up with the definition that language is a set, finite or infinite of sentences, and each sentence is a finite set of elements, and those elements are, of course, words. And so all natural languages, either spoken or written, are languages in this sense, says Noam Chomsky. And so that's a lot more useful for us when we're dealing with computational language or computing natural language. And so we can sum it down to this. What is natural language? It's a set of sentences. Every point I make, every idea I communicate with you guys is in the form of a sentence. It doesn't have to be in a complete sentence, but it's a sentence, and each sentence is made up of words, and each word is made up of characters. And now this all makes a lot of sense to us, but you got to remember, computers don't have common sense. I made this meme here to illustrate that to a computer, a string of text is just a string of text. In order for it to make any sense of it, you got to start programming some algorithms into it. And so what are some of those algorithms? Well, let me get into processing text. Let's say we have a sentence here, or rather a string. The cat sat on the mat. Well, more useful representation of this would be maybe a list of all the words. So you might break it up into the cat sat on the mat. So a list, and this would be a lot more useful to a computer and to us because we're the ones using the computer. And so we call this in natural language processing tokenization, splitting a string into its discrete tokens. This can be words, but this also includes punctuation, because punctuation has a lot of useful information that you wouldn't want to lose. And, that seems pretty straightforward. Does that mean you could just split sentences by white space? And the answer is, of course, there are exceptions. You don't always want to split by white space. There are times you want to split, for example, with suffixes. When we say don't, we really mean do not. So a tokenizer might have an exception for splitting these suffixes apart. Another exception is that sometimes we don't want to split things. For example, the UK. If you just split by punctuation, it'll be U.K, but we want UK to be a individual token. So you got to keep in mind those exceptions. And lastly, there's a bit of a gray area, and this really depends on how you implement tokenization. Hyphens, for example, what do you split on hyphens? Do you keep them? And luckily, you don't really have to worry about this because a lot of the tokenization algorithms have already been programmed to take these into account. But just keep in mind that sometimes there are exceptions that might or might not influence your work. Right, so we can split these words into tokens, but sometimes a more useful way to represent words is to lemmatize them, or also called stemming. And this is to convert words to their base form. Now, why might you want to do this? Well, sometimes you want to convert, sometimes you're not so much interested in the particular tense of a verb. You're just interested in whether the word is there or not. And so words like am, are, is, these are all essentially the same form of the word to be. And so on for car, cars, and so on. These all convert to the base form or lemma, which is car. And you can go on. Color, for example, goes to color because we're in America here. And this is all just a way of standardize the text that you're processing. And that makes it more useful for the computer at times. Sometimes you don't want to do this because you might want to keep the tense or keep your British spelling, but it can be useful. So the next topic I want to talk about is part of speech tagging. So sometimes you want to look at what type of word it is that you're looking at in a sentence. And to do that, you can look at the part of speech. Now, I won't get into how this is done. It's essentially just a statistical model, a predictive model. And what it does is label each token with its part of speech. And that's pretty nice. It allows you to look at, which part of the sentence is a noun, which part is a pronoun, what are the verbs of the sentence. And if you look at how the algorithm's implemented, they'll often give it a tag rather than writing out the whole thing. And these tags essentially translate to essentially this part of speech framework. I think this one is from Stanford. So let me translate it for you. So PRP means personal pronoun. VBZ is a verb. NNS is a plural noun, and so on. And so this is pretty useful. But what if we want to not just look at the adjectives or a particular noun? What if we want to get the adjectives describing a noun? Well, part of speech only tells us what's a noun and what's an adjective. To do what I just described, you need to do something called dependency parsing. Now, dependency parsing extracts relationships between tokens. You want to get the adjectives describing a noun? Well, dependency parsing does just that, and so on for adverbs describing verbs. And this is all very useful. And there's this good demo here, which I'll briefly go over. And it's very cool. You can see how the dependency parsing works. There's a root to the tree here. And each one of these is a tree. And you can click and you can explore how all the words are connected. And this is just, a very cool visualization to understand how these dependencies work. There's these modifiers here, which I'll get into later when we get into our demo. There we go. So I covered a lot of basic stuff. There's a ton of other NLP sentence level tools like noun chunking, sentence splitting, entity recognition, sentiment classification, emotion classification, and many, many more, which I'll briefly get into in our next segment, coding interlude. And let me send out this link here. So we'll take a break here just to do some coding, give you some hands-on experience. And if you click on that link, it should take you to this Google Drive folder, which I've prepared. And the main file you should open is this IPython notebook called HackPSU NLP. I have this option to open it with Google Collaboratory. If you don't have that, I believe you can connect more apps, and that should allow you to open it with Google Collaboratory. If not, you can Google Collaboratory and open it like this way. Let me know if you have any questions getting to this screen, assuming you want some hands-on experience. If not, feel free to just watch, because I have this mostly pre-prepared. All right, Enelson got to the screen. Awesome. Now, this segment does require a bit of Python knowledge, just very basic Python programming. Even if you don't know Python, I think the concept should be pretty straightforward. So just follow along if you don't want to open up Collaboratory. All right, so let's get into some code. So the main library I use for natural language processing is a library called Spacey. And we'll just import Spacey here. The good thing about Collaboratory is that you don't have to worry about installing any packages. It's mostly pre-installed, and that is awesome for data science. So this link here brings you to the Spacey documentation if you want to get more in depth with the features I'll describe. And so the first thing you want to do with Spacey is to load any string that you might have into an NLP object. And this NLP object comes with Spacey, and it does all the cool NLP stuff I just described. For example, tokenization. Spacey automatically tokenizes for you, so you can just run a for loop over this document, and you can just print out the token.txt, and it gives you all the tokens. So that's pretty neat. It also does lemmatization for you. So for each token, you can print out the text and the lemma. Don't forget about this underscore here. Spacey is a bit weird with how it represents the properties. Moving on. So part of speech tags are also inbuilt with Spacey. So as with lemma, you can just print out the token.pos underscore, and that'll give you the corresponding word and the corresponding part of speech. And if you don't know what these tags mean, Spacey has a useful functionality called spacey.explain. And, if you don't know what CCONJ is, you can just do spaCy.explain CCONJ, and it'll tell you, oh, this is a coordinated conjunction. And we can do another one here. Let's do ADP. And okay, that's add position. And you can just Google these terms here. And the next one I want to go over is dependency parsing. And I personally find dependency parsing the most useful if you're trying to do anything meaningful with sort of inter-sentence relations. So for each token, you can print out the dependency type by doing .dep underscore, and that'll tell you that the, for example, is det, a determiner, neural is a mod, adjective, and so on. But a more important thing, I think, is to look at the token.head. And as I mentioned in this demo here, each word has like a sort of parent to it. It's in a tree structure. And so this tree structure lets you look at the actual dependencies. For example, neural is an adjective. You want to get the noun that the adjective is modifying, well, you can do token.head, and that'll tell you, oh, neural is describing this other token, networks. And I'll get into an example of that later. So that's very useful. And again, you can use space.explain to explain any determiner or any dependencies that you're not familiar with. Moving on, so the functions I told you are essentially the basics. They don't require too much fancy statistical models. It's all very straightforward. But the methods I'm about to show you are more, let's say, machine learning oriented. But you don't have to worry about that. You just have to worry about what these models can do for you. And an example of that is entity recognition. So spaCy has an inbuilt entity recognition model. And what this does is it looks at the sentence and pulls out all the entities that are present in that sentence. For example, in that sentence I just gave, neural networks from Google are lit. It found Google to be an org, and you can do space.explain org, and that tells you that it's companies, agencies, institutions, and so on. But we could, for example, do neural networks from Google in, let's say, Delaware. And spaCy should pull out Delaware here as a GPE, which stands for geopolitical entity. So it can do locations, company names, proper nouns, and so on. And you don't have to worry about how it does it. It's a lot of machine learning magic, but it's very useful. And of course, it's not one size fits all. You need a different machine learning model if you're trying to do more specific things. Like, say, if you're trying to read legal documents, spaCy is not going to have like legal terminology built in. So there's a lot of different packages that you should look at depending on your application. But the one spaCy comes with, pretty useful for just general use. Another concept that you might find useful is noun chunking. And so that's just getting noun chunks, not just the nouns, which you might get in part of speech tagging, but entire descriptions of nouns, which includes the adjectives, other maybe compound nouns. And again, the way it does it is a pretty sophisticated statistical model, but essentially it just gives you, spaCy lets you extract the noun chunks. And you can see in this sentence, autonomous vehicles shift insurance liability towards car manufacturers. There are 3 noun chunks here: autonomous vehicles, insurance liability, and car manufacturers. And so that could be very useful and save you a lot of work depending on your application. And lastly, there's a pretty simple functionality, but surprisingly hard to implement one, which is just splitting a text into sentences. And luckily for us, Spacey automatically does that for us using this dot sentences or dot sense property. And you can just iterate over that. And so Spacey will take care of all the exceptions for you, all the abbreviations. It'll hopefully take care of that and get your list of sentences. And there are so many more applications. One brief one that I encourage you to explore on your own, but I'll just briefly gloss over here, is sentiment classification. And so there's this library called Flare. Unfortunately, Spacey doesn't do sentiment classification since it is a more machine learning topic, but there's a library called Flare, and they provide a sentiment classifier model. They call it text classifier. And you can essentially classify strings of text by positive or negative sentiment. So, okay, this will take some time to load, but like you can imagine this text is a positive, very positive text, and then you might get a more negative text, and that might be not so good. And I'll just briefly show you what you can do with that. So my DS340 class, I use Flare to essentially classify a bunch of tweets and to view the tweets, the percentage of tweets that were positive by state. And these were tweets about the election. And you can see here the distribution of positive tweets throughout the United States. And it's just a cool visualization. Rhode Island, for example, is pretty negative when I filter for tweets that mention Biden. And so, yeah, just a brief application of that. Anyways, I want to give you this little demo here. So if you look into the folder I gave you, there should be a tweets.json file. Now, if you download this and load it into your Google Colab, and you should just be able to do this with this method. That should load the tweets data in. Oh, this is taking a bit. Once you get that loaded in, these two blocks here are just converting this tweet from JSON into a Python list. And you can see here, there's just a list of dictionaries. And what we're interested here is this text dictionary or text entry here. And so that's what this block is doing here. And we can display some of these texts. But let's say we want to use natural language processing to get more out of our tweets. Well, the first step to actually working with raw data is to clean it. And so that's what this function does. We're removing the @ signs and the hashtags, removing the links, removing the white space, and so on. And we're actually, in this case, I add a period here because people rarely use punctuation on Twitter. And sometimes Spacey doesn't work so well without punctuation at the end. Anyways, once you run that, you can run the function to clean all the text. And you get this nice and clean version of tweets, no hashtags, no @ signs, no links. And that prepares us for finally working with Spacey. And so in this function here, the goal, the idea here is to get all the adjectives describing a word, as I talked about in the dependency parsing section. So let's say we want to see what people are saying about the election, what kind of adjectives they're using. Well, that's what this function does. So we have a for loop here. We iterate through each tweet. If the keyword we're not interested in this case, election, if that's not in the tweet, we just skip it. If it is, then we continue on. We load the tweet into Spacey. We split it into sentences using doc.sense. And for each sentence, convert to lowercase just to keep things all standardized. Check each token in the sentence. And if the token's head, again, we're looking for adjectives describing the keyword. If the token.head is equal to the keyword and the token dependency type is an adjective, in this case, amod, then we append it to our final data here. And we also print it out. And you can see here when I run this, it'll get all the adjectives that are describing this keyword election. And that's a lot more useful than, say, just getting all the adjectives in general, because this lets you filter for specific relations to a given noun. And you can do all sorts of fun stuff with dependency. Another example here. Oh, wait. Let me first show you this visual here. It's a bar graph I just quickly made. And you can see the most common adjective is presidential, which makes sense. It is a very presidential election that we had. Anyways, yeah, there's a lot more stuff you can do with dependencies. I won't go into this one in depth, but this one's essentially just filtering for a given keyword with a given dependency. So let's say you want to filter for Trump, but you don't want to filter for Trump, in general. You want to filter for when people are talking about Trump, not something Trump did, but people talking about Trump. In that case, you'd want to filter for another dependency type. In this case, it's N subject, which stands for nominal subject. And that just means that the token is the primary subject of the sentence. And in this case, I filtered for all the times where election was described as the nominal subject of the sentence. And I'll just run this quickly. And this is pretty useful for just filtering for useful sentences. And of course, it depends on your application. All right, so that's done. One visualization I like to do with this type of dependency filtering is putting it into a word tree. Now, there's this website here. It's a JSON Davies word tree website, and I'll just copy that. All right. And it's a very useful website to just visualize. Can I copy out here? Copy. I only copied a word. Anyways, I'll just download it then. But yeah, the word tree lets you visualize your text data. Generate word tree. And we'll go to our selected noun here. And you can see it's a pretty neat tree of what people are saying about the election. One phrase per line. This filters it a bit more. And you can just play around with this. Very useful for generating visualizations from, for example, if you're doing a survey, if you're just trying to get feedback from, about a product, Amazon review, any Google survey, these word trees are a great way to visualize that. And of course, you can filter by dependencies if that's useful. So that concludes a brief coding interlude. So with the concepts I talked about just then. There's a lot of things you could do using just those. For example, you can build text monitoring or web scraping applications. Say you want to filter for a certain noun from mainstream news, or maybe on Twitter you want to see what people are talking about, or if someone mentions Bitcoin, what are people saying about Bitcoin? So there's a lot of text monitoring applications you can do with the functions I just taught you. You can also build better chatbots, expand the functionality of your chatbots, because natural language processing lets you not just look at like a given noun, for example, but how a person might be describing a noun, or if a person's asking for a place, then of course you'd want to use entity recognition to detect if the person is talking about a place. So a lot of good applications for NLP in building chatbots. And lastly, you can just build a bunch of just interesting Discord bots or Twitter bots, Reddit bots. Someone somehow, for example, there's this cool Reddit bot called Haiku Bot, and I'm not sure how they detect poems, but you could essentially format people's poems into sort of coherent, or format people's sentences into a coherent poem. And you can do that with dependency parsing with NLP. So yeah, there's a lot of cool stuff you can do with just the stuff I talked about. But let me move on to some more advanced topics, and we'll have some fun talking about this. So sometimes you don't want to, or sometimes your application isn't about any particular sentence, but rather a whole collection of documents. For example, maybe you're not looking at one particular tweet. Maybe you want to look at 1 million tweets or 1 million blog posts. Well, you gotta have some new tools to do that. And one of those methods is bag words. I'll also talk about TF-IDF and transformers, but let me start with bag words. So in order to process a bunch of documents at once, you'll want to find a way to represent that document. And bag words is one of the more common ways. It's very simple. You just take the words in that document and then count them up. So the cat sat, well, that would create a vector 1 with the cat sat all having a count of 1. And you can look at another document, the cat sat in the hat, and this time there are 2 those. And bag words essentially creates this vector, but you can also think about it like a sort of dictionary of your word frequencies. And what you can do with bag words representation is something called term frequency inverse document frequency. Now, this might sound like an intimidating term at first, but it's actually very straightforward. And what it allows you to do is extract the most interesting words from a given document. And how this works is the first term frequency, just represents the amount of times a term appears in a document. So going back to the previous example, if we're looking at the word the, then the term frequency would just be 2 for this document. And so we multiply how many times that word appears with how rare that word is when you take into consideration all the other documents. So for example, an article might have the word the show up a lot of times, maybe 100 times we see the word the. But if you look at the inverse document frequency, if you look at how common the word the is in other documents, it's also pretty common, right? And so when you take the inverse of that, it's like 1 over 1,000 or something, for example. And so that's actually not very important. The word the appears very frequently just in documents in general. But let's say we have an article, and this article mentions cat a lot, and it has like say 100 instances of the word cat. When you look at the inverse document frequency for cat, you might find that wait, cat is actually a pretty rare word. You know, these other documents don't talk about cats; they talk about other things. So that the IDF term here would be relatively high compared with the IDF term for the word the. And so this essentially allows you to find what interesting words occur in a document. And that's useful for all sorts of things, like classifying documents or just extracting the primary topics people are talking about. The last concept I want to talk about is transformers. Now, this is very advanced, or how it works is very advanced, but I'll just let you know what it's useful for. And essentially, it takes in an input or it takes in a string of text as input, and it outputs a prediction of what follows that string of text. So transformers are a function or a method to allow you to predict the next word. And this is surprisingly fun to play with, but there's also a lot of useful applications. And I'll just go over the brief steps or very basic steps of how it works. So it converts the text into a series of word embeddings, which are essentially representations of words that you need in order for machine learning models to actually make use of it, because Unicode isn't very useful for machine learning. These embeddings then go through this encoder-decoder network, which for all intents and purposes, you can just assume is machine learning magic. And lastly, the decoders produce the output text, which is the prediction. And this is a brief visualization of how it can work in predicting. And you can see one application in this little visualization, which is translation. So you can use transformers to translate text. And the way you do that is you have a sentence in another language and a sentence in English, and you can train a model just predicting these foreign languages, translating them into English. And you can train it to predict essentially the English translation of the given sentence. So that's one application. But there's a lot of cool stuff you can do with it. And you can actually make your own text generating model very easily, in fact. OpenAI came out with a model called GPT-2. And I won't get into how it works, but if you click on this link here, and I'll send out this link. That takes you to the blog post describing how you can generate your own GPT-2 model. So you can read that on your own time, but I'll show you in this, in the Google Drive folder I have prepared for you. There's this other Colab file called Train a GPT-2 Text Generating Model with a GPU. And so you can open that in Google Collaboratory. And this is essentially just like a translation of this blog post into Colab. And it's made by Max Wolf. So God bless Max. So you can do some really, really neat stuff with this. Unfortunately, it does take some time to train. So I'll just maybe get this started, but I do have some already trained examples. And the example Max gives is training GPT-2 to generate text like Shakespeare. Right, so you can feed it this Shakespeare.txt file here. And what the transformer model does, which is what GPT-2 is, the transformer will essentially learn to predict how, Shakespeare writes. And then you get this model that can generate like Shakespeare-like responses to a given prompt. But I took it one step farther, and I created this text file called comedy. And what I did with this comedy text file is I essentially crawled a bunch of sites for comedy transcripts. So like from Saturday Night Live, Netflix transcripts, Dave Chappelle, George Carlin, all these comedians, and I copied their transcripts into this text file. And what you can do with GPT-2 is you can train it on a text file to predict. So I thought maybe I can create a comedic GPT-2. And so I'll just go over briefly how you do that. So I've loaded TensorFlow, I've imported GPT-2. You can confirm that you have a GPU loaded. And then we'll just download the 124 model. And the larger models, I think, are generally more complex. They provide more varied responses. But 124 is a good model for just demoing. And the M here stands for million. So this is 124 million parameters for those machine learning nerds out there. And you want to mount your Google Drive just so you can store the model that you train. And we just do it like that. Once you have that mounted, you can upload your file. So let me upload comedy.txt here. You can just drag and drop it into the sidebar here. Again, let me know if you have any questions. Any questions with this Google Collaboratory or in general. Okay, so once you have that uploaded, you can set your file name. And then you can start training. So we have our data set equal to our file name. Model name is a small model. We'll just do 1,000 steps. And let's click train. Let's fine tune it. And this should be setting up everything. Yeah, so what we're actually doing here is we're not training GPT-2. GPT-2 is a pre-trained transformer. And the folks at OpenAI, they already trained GPT-2 on I don't know, billions of pages of Wikipedia or something. And so GPT already has a basic understanding of English grammar. What we're doing here is we're fine-tuning it. And so we're just essentially taking the last layer of GPT-2 for those who are interested and fine-tuning it to the particular text. Right. So we'll let this train and we'll see what happens there. I think there's also a way to set the learning rate. I'm pretty sure you can set the learning rate just to make things go faster. Oh, right, here it is. Yeah, okay. Actually, that's the default, so never mind. But, so Enelson asks, what type of neural network does GPT-2 use? So GPT-2 uses transformers, actually, which is, as I just described, essentially a stack of encoding, decoding layers. And so it uses transformers. And that's the neural network. It's a bit hard to describe in a few sentences, but in a sense, it's just encoding and decoding text. That's what it's training on. But yeah, you can definitely look up transformers. There's a great blog post. Let me link back to this one. So if you click on this link, and maybe I'll send this out for those who are interested. This blog post essentially illustrates how the transformer works. And this is the technology that GPT and probably a lot of chatbots are based on, at least now. I'm sure in 2022 or something we'll have a new architecture, but this is a state of the art for at the moment. All right, so this is training. Okay, so you're just interested in knowing what ML/AL magic it uses. It's actually not that magical. So the way it's trained is it has you're essentially optimizing for something when you have these machine learning models. And what GPT-2 is optimizing for is very simple. It's very simple. And it's essentially just here, I'll go over to this blog post here. Where's a good example? Okay. Yeah, there's a lot of it. I'm trying to find what it's optimizing for. All right, so you can see like this table here. You have a list of words, and all it's optimizing for is predicting the next word in that sequence. And so I'm a student. Okay, that's not a sentence. But essentially, it's just optimizing for what comes next into a sentence. It's a very dumb or very low level optimization. It doesn't think or do any human like logic. All it's doing is just optimizing for trying to predict the next word in a sequence of words. So this is still training. In the meantime, I'll show you what a completely trained or completely fine-tuned GPT-2 network looks like and what you can do with this type of technology. So in one of my projects I did for fun, I just took this GPT-2 model that I trained on comedy transcripts, and I made a way you can ask it questions. And I turned it into a Discord bot. So anyone on my Discord server can ask this bot a question, and it'll try and respond to the best of its ability. And this code is pretty messy. Maybe if I get the time, I'll put the cleaned version up there. Right, maximize the. I don't know about the probability. It's like trying to maximize the correctness, like the proper way to predict the next word. But yeah, that's essentially it. So I made this Discord bot to ask GPT-2 questions, and and you can, and I called it Marcelo. But anyone in the audience want to give me a question, any question, literally anything, just give me a question, and I'll ask the GPT-2 network what it thinks. Any volunteers for a question? What is the meaning of life? Okay, that's a good one. So ask. Right. So ask this bot, what is the meaning of life? And remember, this bot is trained on comedy transcripts, so there might be some profanities, some swearing, but it's funny, right? All right, so it's running on this command line here.
Life is just another idea created by the intellect to confuse us. Life is just another idea that somebody else created. Marcelo said life is just another meaningless idea. Life is just a meaningless concept.
So you can see it's pretty repetitive.
It's just an idea invented by somebody else to confuse us. That's what life is. Marcelo said it's just a meaningless idea. But God is better than all these ideas.
All right. Anyone else have another question?
Worth worshiping.
Who's on first?
God is better than all these meaningless. Marcelo said ideas. God is the only God worthy of worshipping.
You're right. You can actually, let me show you another thing you can do. So you can set the temperature, and the higher temperature that you set, it makes it more crazy essentially. So I'm curious what happens if I set the temperature to 0.95. So Ryan Webb asks, who's on first? So hopefully it's a bit less repetitive since I raised the temperature setting. But let's see how it responds to Ryan's question. My dear friends, what a nice weekend we had. Yeah, this one's a bit more comedic, not so depressing like the last one. But yeah, you can play around with this once you get your own model trained up. And the notebook gives you instructions on like how to generate text, how to save your models, how to query it. So yeah, in your own time, you can play around with GPT-2, see what you can do with it, see what kind of meme bots you can make. But yeah, that's about it for my workshop. I think we're out of time here, so thank you all for coming. Hope you learned something new. Hopefully you can do something cool with natural language processing, and yeah, just make some cool stuff. Happy hackathons.
Virtual applause for Thomas. Thank you for coming. That was great. We appreciate it.
Thank you.
All right, I'll let everyone get to their next workshop, and I'll see you soon.
See ya.